questions from previous years. Okay, so that's a good idea. You can get a good idea of what kind of questions you may expect from the practice material. But that is like still eons away, so let's not trouble our pretty little heads with this kind of stuff. Instead, we're going to focus on today, and today is a wonderful day, I can tell you that, because I'm going to throw in, for the first time in this lecture, an actual molecule, okay? Isn't that great? Yeah, all right. Before I do that, though, true to form, I'm going to go through some stuff that you probably already know. I just want to make sure that everybody is on board with this, and that has to do with complex numbers. You already noticed that complex numbers play an important role. You don't like it? Somebody's shaking their head. Said, no, 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 I don't want to know anything about this. Don't tell me anything. It turns out it's actually important, so some sort of familiarity with complex numbers is really helpful. So, as you know, I squared equals -1. That is the definition of the complex number I, okay? So if I would take the square root on each side, I would get this, right? And since the square root of something that is squared is just the number itself, I can write I equals the square root of the -1. So the first line and the third line basically are the definition of what I is. So what if I have something like this? What if I have a number that is negative and I'm forced to take the square root of it? And we have already seen something like this. Actually, last lecture we did it. We had a k squared with a negative sign in front of it, and we were taking a square root of it. So you may not recognize that now, but I will get back to it in this lecture again. And so we have to be somewhat familiar with these kind of situations. So let's say I have a number. A is a positive number, okay, and then there's a negative sign in front of it. So the whole thing, -a, is definitely something negative. So if I take the square root of that, how can I solve that problem? Well, since I know that -1 can be written as I squared, okay, I can write this thing as I squared times A, and then the square root. All right, and so since I can write the square root of a product as 2 square roots, okay, that's fine. So I get the square root of I squared and then the square root of A. So that thing is nothing but I times square root of A. Right? So that's good to know, because every time I see the square root of a negative number, I can just write it in this way. I times the square root of the number, and I said A is a positive number, which is totally fine. I can take the square root of that. All right, keep this in mind, we'll be using it. Second, of course, definition of a complex number is, let's call it Z equals X, which is the real part, plus the imaginary part, which is I, times Y, where Y is the value of the negative, of the imaginary part. So the real part of Z is, of course, X, and the imaginary part of Z has the value Y. Okay, so this is really the definition of a complex number, which contains both real and an imaginary part. So this, of course, is something we have seen already quite a bit. The complex exponential function, a critical function in quantum mechanics. And if you write that in the most general form, which is e to the power ix, then I can always write it in this way. That is the cosine of x plus something imaginary with the value sine of x. So the real part of this function is a cosine of x, and the imaginary part of this function, of this complex function, e to the power ix, equals sine x. So that's the imaginary part. So the real part, imaginary part of this function, I can recognize. this is something we have seen also already. Okay, and you probably know that this thing equals 1. But why is that so? Well, you can quickly prove it to yourself. If you forget, you can quickly derive it. Because I can write this expression in the following way. If I have a modulus squared, the thing in between, what I have to do with it, I have to multiply it by itself, but first I take the function and then multiply it by its complex conjugate. So that's what I'm doing. The function itself times the complex conjugate of that function. The complex conjugate is nothing but the function, and then everywhere an I appears, a negative sign is added. Okay, so that's the complex conjugate of that function. So what I'm getting is the product of these two things. And I can rewrite that because I can just combine the powers of each in the following way. Right? The powers I can just add up. So it's e to the power I, between parentheses, x minus x is of course 0. So I get e to the power 0, which is 1. Okay, so the nice thing about this function, of course, the modulus square of a complex exponent, no matter what is in the exponent. Okay, x could be anything. As long as x is real, that's important. If x is real, then the modulus square of this quantity equals 1. Okay, here's another one. Now the complex exponent is having as its power I 2 times n times pi, where n is an integer. What is this? Well, I can write it in this way, always. So I just fill out for x. X equals 2n pi. So I get cosine 2n pi plus I sine 2n pi. What is the outcome of this? Well, I know that every time I have the value 2 pi times an integer, and I take the sine of it, I get 0. So the imaginary part crosses out. The real part, the cosine part, every time I have 2 pi of the cosine, I get 1. So this thing is 1, always. No matter what n is, it's 1. How about this? 2n plus 1 times pi. What is that going to be? That's negative 1. Because the sine is still 0, but the cosine now is negative 1. So these are good things to keep in mind. Every time we see something like that, we know that complex exponent is actually very simple, has a very simple solution, namely 1 or negative 1 in these particular cases. Finally, I can write the cosine function and the sine function in terms of these complex exponents. Namely, the definition of a cosine, written in terms of the complex exponent, is this: 1/2, and then between parentheses, e to the power ix plus e to the power negative ix. Okay, hopefully you're familiar with that. And the same for the sine, where instead of having half, I have now 1/2i. That's important. And then a negative sign, where previously was a positive sign. Okay, so e to the power ix negative e to the power minus ix. Okay, so the last expression here, the sin x one, I will use today. Okay, so we will be implementing it right now. Okay, so here it is, a molecule, folks. Finally, you can stop hating me now. I am really in the Department of Chemistry, so let's look at this. Beautiful molecule. But what we're interested in here is something in particular, because this molecule, as you can see, by the way, this is retinol. Okay, it doesn't matter, but that's what it is. You see that it has a whole bunch of conjugated double bonds. You see that? Let's see, 1, 2, 3, 4, 5. 5 double bonds, and they are in conjugation. That means alternating double, single, okay? Now, if you are an electron, and you happen to be in one of those pi orbitals, then actually you are able to travel along this conjugated track, right? You know that. It's called delocalization. Conjugation means the electrons in these pi orbitals can actually move along. So an electron is basically somewhat free to move along that track. Okay. Now, interestingly, the fact that the electron can do that assigns really nice optical properties to this molecule, okay? As you will see today. And we're going to study that. So I'm going to try to model this behavior of the electron along that track. How? I'm going to say the following. I'm going to say that the electron is confined to this track in one dimension. I can just see this track as a one-dimensional track, okay? So it makes a little corner there at the end, but it doesn't matter. I'll just imagine it's just like x. I can just travel x from 0 to the length. 0 to L, that's the track, one-dimensional track. The electron, if it's part of the pi conjugation, can move. So it cannot move beyond that, and that's why I'm going to put a barrier, V, which is really high, infinity, aka the electron can't go there. And on the other end, the same story. The electron cannot move beyond these barriers, it can only move along a track. This is a one-dimensional problem of motion of an electron. Okay? Very good. So, simplified, it looks like this. I have a track from 0 to L, it's one-dimensional. A simplification, of course, but we have to start somewhere. It's the simplest one I can do, and it still makes a lot of sense. And then, at the end of the track, I have a barrier, simply meaning the electron shouldn't go there, and here, there is another barrier, the electron shouldn't go there. In between those barriers, there is no potential obstruction. The electron doesn't feel there is a barrier in between. It can freely move. V equals 0. Potential energy barrier equals 0 between 0 and L. Okay, now what do I know? Well, I do know the electron behaves like a wave, folks. So, that means I have to find the wave function of this electron in this one-dimensional track, on this one-dimensional track. And I know, because we solved this last time, that the wave function in its most general form looks like this. This is the most general form of an electron that moves along a track where there is no potential. You can go back to the lecture from last time, and you'll see that if V equals 0, then this is the solution. And therefore, I'm going to just say that is the solution of the electron in this area. Of course, what about these areas? The gray zones, what happens there? What is the wave function in those regions? Well, we also saw that last time. We saw that in those regions, it looks something like this. It's not a k, where k is a positive real number. In fact, it is now negative kappa x. The kappa was defined last time. I'll show it to you again. Okay, but kappa is a real number, but now there's a negative sign. The I is gone. And so this is a decaying exponential. So in this barrier, it decays to 0. All right? That's what I want. I don't want the electron to go here. I want it to disappear and its amplitude to go to 0. That's what I want. On the other side, I want the same thing. So the wave function on the other end looks like this. Why is there no negative sign? Because the x goes this way towards negative numbers, and therefore that's also a decaying exponential going to 0 in this direction. So this is the most general form of the wave function, and there's a lot of things in there that I don't know what they are. I don't know what A is. B, C, and D are not defined. Kappa is not defined in an actual number, and K is also somewhat abstract at this point. But this is the general expression. So my goal is now to find those missing pieces. Okay, so what is K again? K is this. K is this. So Can always be written in this way. It says the square root of 2m e minus v, and then divided by h bar. And if the potential equals 0, so when v equals 0, that means the middle of the box, okay? Then this thing is definitely going to be a real number. Because E is a positive number, you can only have positive energies, so the whole thing is going to be positive, no problem there. The problem, of course, happens when V is larger than E, and that's the case with these barriers, because the barriers are infinitely high. Okay? That means if V is infinite, then that thing is going to be negative. The thing that's in the square root is going to be negative. That's a problem. And that's why, that's what we did last time, we're going to write it slightly differently. We're going to write it like I kappa, where kappa is a real number. A real positive number, which is written in this way, this particular way, because I switch V and E, okay, so that V is larger than E, and therefore kappa is real and positive. And so K has a negative value under the square root, but I'm rewriting it in terms of I kappa, just like on the first slide of the presentation, where I had an A. The A is now your kappa. The kappa is defined as something positive, all right, with a negative sign in front of it. I take the square root, I get I kappa. So that is that connection right there. I use that trick. I use the trick of a negative number, take the square root, I get I times the negative number, where the number itself is a positive quantity, either A or kappa. That's how it's written. Okay, so I have these kappas. These kappas are relevant in those gray zones, right? Where I get these decaying exponentials. What does it look like? Well, I have now an expression for kappa, and now V is infinite, so when I substitute it, K becomes infinite too. Sorry, kappa becomes infinite too. If kappa becomes infinite, what happens to this decaying exponential? Well, negative kappa times x. If kappa goes to infinity, then this this exponential goes to 0. Does that make sense? When kappa goes to infinity, the decaying exponential goes to 0. So that means something like this. If you think about this picture, the gray zones are again the areas where you have infinite potential. As soon as you hit this region, kappa is going to be 0. So as soon as you hit this region, the amplitude of your wave function has to go to 0. Okay? That's what it says. E negative kappa x is 0. At this point, I have that function, E kappa x. Kappa goes to infinity or negative infinity, and that means I get 0 right there. So in the box, I can have a waveform, but as soon as it hits the edges, it has to be 0. In the potential energy zone, it is flat, meaning there is no amplitude, aka the particle is not there. This is just code word for saying the particle can only be in the box, in this track, on this track, but it cannot be in the zones. Therefore, the wave function must end at 0 at those points. For all waveforms I stuff into the box, I can say that at the edges of this track, the amplitude has to go to 0. Otherwise, it's going to be in the box, outside of the box, and then I just said it can't go there. Okay, so what I have then is this situation one more time. In between 0 and L, it can have a finite value. So let's look at the shape, the form, the values in that region. What can I say about K? Well, the definition of K was given. When V equals 0, K is the square root of that. So the square of that, K squared, equals 2m times E over h bar squared. In the region between 0 and L, that is the value of k. But since the energy is in there, I can also write this in terms of the energy. I can write the energy of the electron when it's sitting in that box is k squared h bar squared over 2m. It's kind of nice, because now I have actually an expression for the energy of the electron. That's kind of what I would like to know. I would like to know, what is the energy of the electron when it's there? Well, there. That's the most general answer. It's k squared h bar squared over 2m. Sounds great, but I still don't know exactly what the real values of k are. Can we get to that point? Okay? This is a general expression of energy, but I'd like to specify what are those specific values of k, so I can actually say something a little bit more about what the energy actually is. So how do I do that? What I'm going to do is, I'm going to be a little bit more zooming into the problem and see what happens at the edges, or the boundaries of this box. This is basically solving the so-called boundary conditions of this problem. Okay? I'm going to solve the problem at the edges of my space, 0 and L, and I'm going to use what I just concluded. Namely, if I look at the point x equals 0, I can tell you that the amplitude of the wave function must be 0. That's what we just concluded. Okay? So, that means if I fill in for x the value 0, that means that psi at 0 must be this. Okay? It must be a times and then the complex exponent, but x equals 0, and the same for the b term. So what I'm getting, since the complex exponent at 0 equals 1, I simply get a plus b. So at this point, x equals 0, I get the answer that the amplitude of the wave function equals a plus b. But I just said that it should be 0 there. The amplitude should be 0 because the particle needs to disappear there. It can't go there. Therefore, a must be negative b, right? Or b must be negative a. It's the same. B must be negative a, so that I know for sure that the amplitude of the wave function goes to 0 at the edges, at x equals 0. So what I'm having then is the following. I have the following. I can write now b in terms of a, and I got rid of the b. So that's good. One of those constants is gone now. It's now defined in terms of a. And I can rewrite that just a little bit by taking the a out. Okay, so you see something nice appears. If I take the a out of this expression, I get a times, between parentheses, a complex exponent with then the same function with a negative sign in front of it and its complex conjugate. That looks like a sine wave, as you will see in a few seconds. Let's look at point L, which is the other end of the track, where I have the same condition, because also there, at that point, the amplitude of the wave function must go to 0. Okay, so I'm going to use my new form now, over here, and I'm going to say, when it's L, when x equals L, this thing must also be 0. I'm going to take the a out, so I'm going to write it as such. Okay? And, again, look at this. This looks like a sine function, right? Remember that? The definition of the sine function in terms of complex exponent is like this. Okay, so I'm going to use this definition of the sine function and rewrite the wave function in terms of a sine. So what I'm getting is this. It's 2i times sine KL. The 2i, of course, comes from this. Right here. There's 2i here. 2i is not there, so therefore